Your urine versus urine. So welcome to the final STEM Enhancement in Earth Science student presentations. We have had hardworking students that worked remotely with their project scientists for 2 weeks prior to coming to the University Center for Space Research. And then they have been working diligently for the last 2 weeks here on site. My name is Margaret Baggio. I'm the Senior Education and Outreach Coordinator for NASA's Texas Space Grant Consortium, and we are housed here at the University of Texas Center for Space Research. The Director of Texas Space Grant is Dr. Wallace Fowler, and Dr. Fowler and I are the ones that submitted this proposal to NASA for funding to expand the high school internship program that we've had here at the Center for Space Research for the past 5 years. So we were fortunate that NASA wanted us to not only continue but to expand this program. We want students in Hobart, Alaska or Poteet, Texas to be able to work with scientists and engineers analyzing Earth-observing satellite data from NASA's fleet of satellites. So our projects this year were divided into 7 teams, and our first team today has been working on astronomy. So they will introduce themselves, and at the end you'll have an opportunity to ask a few questions. So we're ready for our astronomy team.
We're the astronomy team here at the NASA Seas High School Internship Program. My name is Morgan Nanez. I live in Austin, Texas, and I'm going to be a senior next year at Vanderbilt High School.
Hi, I'm Colette Duran. I'm also going to be senior, and I'm from South Salem, New York.
I'm Chidema Agba. I'm from Los Angeles, and I'm going to be a senior at Norwalk High School.
I'm Alessandro Cartegni, and I'm going to be a junior at Stuyvesant High School in New York City.
Hello, I'm Brian Zinn, and I'm going to be a senior at Lowell High School. I live in San Francisco, California.
So because astronomy is such a broad topic, we focused on one section called Astrometry, and it combines mathematics and the laws of physics to study our universe. Astronomers catalog astronomical bodies, and these catalogs not only help them to track them, but to also discover new ones, because these bodies can be used as reference points in the future, which we'll touch on later. It's important to be accurate with your data, and data can be used to, in regards to location. If we know the location of an astronomical body, we can also find the origin and discover more about its kinematics.
Okay, so the first thing that we did when we got here was discuss parallax. So parallax is the difference in the apparent position of an object viewed along 2 different lines of sight. So just as an example, so if everyone could put their thumb up. Okay, so if you close one eye, you can notice what's behind your thumb, and if you switch and close the other eye, then the objects behind it seem to move. That's parallax. Awesome, okay. So you measure parallax by the angle between 2 reference points, and you cut it in half. So we use this in astronomy to find the distance of astronomical bodies.
So, in our 2 weeks at NASA, we tried to simulate the process of the parallax. So, we used a styrofoam ball as a star, and we mounted it on a tripod. And so we put that tripod on one end of the room, and then on the other end, we have our 2 reference points marked by 2 lines of tape. And then, so at these reference points, we look towards the far end wall at a reference star, as we pointed out over there. The reference star is an infinite point beyond the wall. And so the math behind the parallax, here's the math behind the parallax. And it gets a little bit tedious, so just bear with me. So A and B are our 2 reference points, and then C is the object that we're trying to find the distance to. If you draw a ray from point A straight up, then you get ray A, and what we did is we measured the angle made by ray A and point C. So that's angle 1. And then we did the same for the second side, ray B and point C, angle 2. By its geometry, angle 1 and angle 2, if you add them together, will equal angle C. And so if we enlarge this triangle ABC over here, we get this picture. What we did here is that we dropped a perpendicular line straight down from point C to line segment AB. What this does is that it divides angle C in half, and it also divides line segment AB in half. Now we have a triangle, ACD, and now we've enlarged it over here. This triangle is a right triangle with right angle angle D, and we have half of angle C, which is the parallax that Morgan was talking about. This allows us to find the distance CD by using the inverse tangent of angle C and dividing it by AD.
So in the actual experiment, we had 2 methods of trying to determine the distance. I'm going to explain the first one that we used here. So we used this measuring object here. I don't know really what to call it other than that. It's a protractor with extensions. And how we used it, we had to see this. This is the styrofoam ball about 10 meters away from us. And the back wall was what we were having the reference points be. And so using this object, we were able to center it on the object and then find the different angles like this, right? This is actually an improvement on the previous design. The previous design was only used a short segment of straw about this long without even having this one, and it caused 2 problems that were solved by this one here. First problem being it wasn't really precise. Since it was so short, it was kind of hard to get the exact angle you were looking for. So having it long like this allows you to really get those like 0.2 degrees that you need. And the other thing is that being long, it allows you to have both the object and these pins here, which are what you use to center it, in focus at the same time. And since they're in focus, you're easily able to point it. Otherwise, it gets difficult.
Our second method for evaluating the parallax angle was something called a modified crossstaff. So a crossstaff was one of the first instruments used in evaluating parallax problems. As you can see here, it's slightly different than the traditional parallax, thus earning the name modified, as the window of observation is horizontal rather than vertical. In using the crossstaff, the observer holds the crossstaff up to their line of sight and then moves the window back and forth, such that the edge of one of the edges is aligned perfectly with the point of reference, and the other edge is aligned perfectly with the target. And using simple geometry, one can determine the angle of parallax as the length of the window remains fixed, and you can easily see what the distance between your eye and the window of observation is for the perfect alignment. Although it's conceptually simple, this actually proved to be an extremely difficult method of measuring the parallax angle. It's extremely difficult to calibrate and was just generally cumbersome to use. We went through several different variations with different window sizes, but nothing really generated a result that was even remotely precise. So we decided that the original design created by our group was actually the more user-friendly device, as it yielded more precise results. In spite of these general issues, the parallax problem was a really essential experience for our team, as it challenged us to exercise both our design thinking and our understanding of the proportions of the sky. Additionally, it allowed us to place ourselves in the perspectives of classical astronomers who used somewhat antiquated ways to find really complex and really precise measurements. And it also showed us how the star catalogs that we base our own data on evolved over time.
Another topic that we focused on during our 2 weeks here was asteroids. So this is the orbit of Jupiter, and this is the orbit of Mars. And most asteroids lie in the asteroid belt, which is between them. And asteroids that follow the orbit of Jupiter are called Trojan asteroids. And the asteroids that we focused on are called near-Earth asteroids because they're near Earth, which is the green dot. I should note that the center of the Trojan asteroids and the Sun create a equilateral triangle, and also that asteroids are not composed mainly of ice, they're composed mainly of rock, and comets are composed mainly of ice.
Another common misconception about asteroids is this kind of trope you see in a lot of science fiction movies in which a ship is like constantly being bombarded by asteroids. That is completely incorrect. Asteroids are actually very sparsely spaced. For most asteroids, which are larger than half a kilometer, there's a minimum of 60,000 kilometers to the next asteroid.
So what our focus was near-Earth asteroids. And so the first thing you have to do is know where to look for these. So you can't just look up in the sky and say that's a near-Earth asteroid because it's hard to calculate that. All right, so thankfully Dr. Reese allowed us to use her images that she took in 2001 at the McDonald Observatory. And we went through all of her logs and we looked for 3 things. First, is it a near-Earth asteroid? Second, are there 3 images in succession that we can use? And after that, we had to look to see if the exposure was over 300 seconds. If it was lower than 300 seconds, then it could be too faint for us to notice, so it has to be above that. And then after that, we put in the declination and right ascension, which is the astronomical equivalent of longitude and latitude. And we put that into the minor planet checker. And from there, we got results for pre-discovery. A pre-discovery is basically an image of an asteroid before it was actually discovered. So, so what we had to do is we got the results, and so if we found something that was equivalent to it in 2013, we know that we had found a pre-discovered asteroid. So Alessandra's going to tell us how we use the 3 images to find the asteroid.
Okay, so this here is an animated GIF of 3 exposures, and what it does is basically you use it to look for asteroids. So the first step you have to do is to center all of the images in the same spot using the stars, which are far enough away that they don't move. So I think we used like this one here as the centering point, and then all of the other stars are in the same places. That's what these green circles are cataloged stars that were recognized by the computer program, which allows it to really pinpoint where you are in space. So in this image, there are 2 asteroids, and I want you to take a moment to find them. An asteroid is generally anything that moves in this image because stars, again, don't move. So if it moves, then you have to check 2 more things. Whether it moves in a straight line, which you can do with like a straight edge on your screen or here. And the second thing, it has to move roughly the same amount. Since the exposures are equivalent in length, they should move the same amount between exposures. So the 2 asteroids in this image are this one here, moving across like that, and then this one here, which is much fainter, moving up like that. And so the 2 red circles in the middle here are actually computer predictions of where this asteroid here would be based on some orbit data. And Dr. Reese was looking for that asteroid there. The reason these are off is really that the orbit data was not very precise, and that's one of the major reasons you want to do these pre-discovery observations, is to really pinpoint the orbits of these asteroids in a way that you can find them years later, even when, as of now, you might not be able to because the orbit is not very precise.
Okay. As pre-discovery data is extremely important in determining the orbit of an asteroid, all of the asteroids that we were able to classify as potential pre-discoveries, we are submitting to the Minor Planet Center. As you can see up there, we're listed as measures, which is kind of cool, as we will be helping forward this field. And you can see that they're taken in groups of 3 exposures because that's necessary to determine a pattern. And 711 is the McDonald Observatory code, and then The data in the center is the right ascension and the declination, and all of this information, if it is approved by the Minor Planet Center, will potentially help astronomers determine a consistent orbit for these asteroids.
So prior to arriving here in Austin, we were all assigned a project to do. So the experiment started at around 10 a.m. on a sunny day, and we put paper on the floor, and we had a gnomon in the center. And basically a gnomon is a thin pole-like structure that casts a shadow, and we would mark the length of the shadow, and we would also document where the top of the gnomon would lie on the paper. And we put that data into the computer, and we created a graph. And this is the gnomon, the setup. Those are the marks that were made throughout the day as the shadow moved. And the highest point in the graph is the solar noon, which is not necessarily 12, but it can be around 11 or any time when the sun is at the highest point in the day. And so using the altitude of the sun and the declination, we were able to find out our latitude, and we were able to also use the Greenwich Mean Time and our solar noon to find our longitude.
So, telescopes. More precisely, these are Dobsonian telescopes. Dobsonian comes from the astronomer John Dobson, who was the person who invented this telescope. The Dobsonian part of this telescope, these are finished Dobsonian telescopes, by the way. We made these last week on our own. We spent about 10 hours on them, so it's pretty long. So the Dobsonian part of this telescope is the box and the axle. You can't see it on here, but there's an axle in here. The axle helps it move around so that it can aim at any point in the sky, and the box holds the telescope in. Now, there's a second part to this telescope, and it's the Newtonian Mechanics. The Newtonian Mechanics consists of three parts. The primary mirror, the secondary mirror, and the eyepiece, which has a magnifying lens in it. If you were to have this encased in a telescope, it would be projected that way. So the opening would be over here. So what would happen is the light would enter through the opening and strike the primary mirror. Now, the primary mirror is a concave lens, so it will absorb the light, collect the light, and project it towards the secondary mirror. The secondary mirror is slanted, and it's for a good reason. It's slanted because it then moves the focus upward towards the eyepiece so that you can see the image. So light hits the primary mirror, bounces off, focuses on the secondary mirror, and then hits the eyepiece, which allows you to see a magnified, higher resolution image of whatever object you're looking at.
So before we go into personal reflections, we'd like to thank a few people. Dr. Reese, we'd like to thank you for being our mentor for the past few weeks, and Mrs. Baggio for setting up this whole internship. And then we'd like to thank the CSR teachers and staff, the Texas Space Grant, and NASA for supporting us throughout the past few weeks.
Can I say something? I would like to tell the group that you only see a few lines of data, but they actually went through my logs from 2001 to 2003 and pulled out a lot of data, and they did some chunk, and I'm thanking them for actually helping me to get a good start on this, and I will continue the work they started. And as soon as I get some magnitude estimates, I will send it to the Minor Planet Center, and I do hope that these observations will be published, and if they will be published, I will tell you guys. So thank you for the great work.
Thank you, Dr. Reese.
So for me personally, I'm interested in astrophysics and theoretical physics. And so being a part of this astronomy team has really opened my eyes to a whole other side of astronomy that I never thought of. And then being a part of the whole NASA internship, it's also shown me that there's a lot of different aspects of NASA. A lot of people tend to think that NASA is just rockets and sending things into space, and it's much more than that. There's chemistry, biology, geologists, it's everything, and it's really cool and really neat to see how it all works together.
Yeah, I also have to echo Morgan's sentiments. It was really interesting to see how all of the different disciplines interacted at NASA. Like personally, I'm very interested in chemistry, but I want to do something related to space, so it was very fascinating to see how, even though I would be entering a field related to space, I could still apply my knowledge in chemistry. Additionally, I really enjoyed just seeing how an actual astronomer works. I've been to a lot of a couple previous astronomy programs, and they've just been very focused on observational astronomy, not crunching data, not using IRAP, not coding. And this was an extremely fascinating experience, and it made me feel very confident about my own abilities and just working as a team. It was a great working as a team, and we really pulled through in some difficult times in the Parallax and other areas such as Mars Bound, and yeah. And
If you want to explain what that was.
I think Shayla's going to explain it slightly. And it was just also a really great experience because there was parts of astronomy that I didn't connect. Like initially I didn't connect the Parallax to the star catalogs and then to the catalogs that we actually use for the asteroids. So it was nice to see how multifaceted everything was, and it was just a unifying experience for me.
Prior to coming here, I had limited knowledge of astronomy, but coming here, right now I can honestly say that I know a lot about astronomy and just teamwork in general, I think. In terms of astronomy, like with blinking images, it's weird to be in like an astronomer's shoes and actually know what they do for a daily basis. And doing that actually made me look at astronomy more as something I might want to do in the future. And with teamwork, when we did Mars Bound, that was really difficult because we're all from different parts of the United States. We all have different mindsets, and we're all creative and have our own ideas. And we all, some of our ideas like conflict with each other. So some of us can get stubborn and don't want to change our minds with something. And so having to learn about compromise and communication, seeing how things might have changed if we were more wanted to compromise, and but I think that's something I'll take with me in the future when I'm doing other group projects or just working with others and seeing how I can work with them better.
So for me, maybe the best takeaway is really, again, how NASA is really a very large organization, and it's not just sending people to the moon, sending the rovers to Mars, or even looking at deep space objects with like something like the Hubble Space Telescope. There's a lot more to that, especially on Earth. NASA is really helpful, and the other groups will elaborate much more on this, I assure you, on how life on Earth goes on and how the climate change goes on, and like responding to problems with hurricanes and stuff like that. And this is really not one of the main things NASA is known for, but it's probably one of the most important. And so another thing I really enjoyed in this experience was when we went to the Johnson Space Center. And I'm sure a lot of people here found that extremely interesting. It's one of the coolest things I've ever done. While I've been to the Kennedy Space Center in Cape Canaveral, it's really not comparable. It's the Johnson is so much bigger. We actually got like to go inside the labs and look at the inner workings of it, and it was like super cool. So yeah, that was awesome. And finally, the work we did I found very interesting, especially because it's real data. This is actual images. These are actual images that were taken, and this is actual data that's being sent to a database, which might help people in the future. So we're not just doing an exercise just to do it. This is real helpful data, and Dr. Rees pointed out that earlier. And so while we didn't find like an Armageddon-style asteroid coming to destroy Earth, it's important nonetheless. So, yeah.
These past 2 weeks here at NASA have been the most life-changing experience I've ever had. I can say this with pride because I've learned so much and made so many new connections with my fellow interns, my team, and my scientists, all of you. This incredible laughter-filled adventure has taught me a valuable lesson that astronomy is not just a subject that scientists can learn, it's anybody, regardless of your background on the subject. Nothing illustrates this fact more than when we built the telescopes. I'm fascinated by that project because we took seemingly random pieces of bolts and wood and converged it together to create something truly spectacular that can look deep into the universe. Personally, I think this emphasizes the value of teamwork, strategy, and intellect that's required to make anything truly outstanding. Not only has NASA SEAS given me the experience of working in a professional lab environment, it's also helped me determine what major I want to be working in when I'm going to college. During my 2 weeks in Austin, I've cultivated new friendships with all my interns and my scientists here. This program has opened my eyes to the options that University of Texas has to offer and the opportunities that it can give me. All in all, I'm glad to be a part of this outstanding program, and I'm glad that I can contribute to what NASA's been doing. Thank you all for making this possible. I'm truly grateful.
It's always tough going first, but y'all did an outstanding job. So if anyone has questions, please direct them to your students.
Were you able to determine the size of the asteroids?
Well, so in our little experiment with the styrofoam ball, we were able to determine the size based on the distance we got and some math. So yes,
And we could use that to actual size.
yeah, it's the same concept,
Yeah.
just a small scale.
If I may add, it's kind of complicated because on the image you see, you only see different, it looks like different size of spots, but that really not size, it's brightness. So what you can do at first is you measure the brightness. If you got the orbit, it means that you know the distance, and then since you don't know anything, you can make reasonable assumption it reflects this much light. So if I know how much light it reflects, I know I can figure out the size. So it's really hard to determine directly, especially the little ones I took. You have to kind of make assumptions and use your laws, your knowledge of physics. But this is a totally different ballpark just from finding them. That's why we don't have the brightness yet. I have to go back and figure those out myself.
And one of the astrometric photographs, did anyone notice the still photograph had what looked like a complex satellite going across?
Well, that was an airplane.
That was
an
actually
airplane.
It could have been a couple things, like they said, an airplane, but it also could have been interference because at McDonald Observatory there's a fair amount of radiation. But
He's
yeah,
talking about why.
that one is an
That's an
airplane.
airplane.
Is it fair to say that it might be an alien?
I don't know. It's not
Well, we
clear.
can't comment on that right now.
That's classified.
Insert X-Files.
Well, Skyler, I thought that those UFOs move much faster. I thought those UFOs move much faster.
I mean,
I don't know.
You could figure it from that.
Well, doesn't matter.
The agency can either confirm or deny that statement.
We'll take no further comments. No, I'm just kidding. I'm just kidding. Yes.
so could you explain Mars Bound and tell us your experience
Mars Bound was a complicated project, to say the least. It required a lot of collaboration. It required a lot of consensus, and that was something that was hard to come to in the beginning. However, we made sure that in the end that we worked together, literally, with not just with each other, but with other teams in order to make sure that our project went off.
Yeah. So background on Mars Bound, for those at home or those in the crowd that don't know, Mars Bound was essentially a theoretical mission. We were given a budget and we had to get to Mars and have some sort of scientific return.
But it wasn't all that simple because sometimes people will take money away from
Yeah.
you. You don't know why, and you totally have to change your project around.
AKA
And
that
then next thing you know, you have to take off your rover and replace it with the lander, and then you don't have enough money for that. So then you're like left with the satellite, and then you don't even know what you're doing anymore. Not from my experience, but
And apparently this is pretty accurate to real life.
yeah, it showed us how real life was, and I mean, I guess it was a good experience. I guess. No, I'm just kidding. It was a good experience. I got to see how like NASA funding actually affects how projects are actually made, and it actually showed me how I guess real life is, even though it was brutal. But
What's the saying about you don't truly learn until you feel frustration?
that was accurate.
So maybe that's
That was
what
pretty
it was.
accurate.
Okay, any other questions?
Delia, how much money did you get taken away for that project?
$75 million.
Yeah.
You're welcome.
I think we had the most taken away in this
We
entire
did.
group.
Yeah, but we ended up partnering up.
And they also had to go to Congress and give a presentation to Congress about their mission to see if their mission would be funded.
Oh yeah, and they didn't fund our mission.
Yeah.
We should point that out. They didn't like it.
Yeah. So it
Well,
was
they did after we did a little bit change. Yeah. They didn't fund it immediately.
It's pretty sad.
It was demoralizing.
Okay, last question. Terrific job. Thank you all very much.
Hey, quiet down.
So are we filming it?
Do you want me to?
For those